Jump into chapter 6, and it starts with discrete random variables. So remember, I guess we don't know this, but a random variable, as defined in statistics, is a numerical measure of the outcome of a probability of an experiment. So if something has a finite or countable number of possible values, we call it discrete. Right, we learned that back in chapter 1. Values could be listed without skipping any. So maybe it's like 0, so it's like the dot at 0, a dot at 1, a dot at 2, dot at 3, dot at 4. Remember, if we have all the values between that, so you have infinitely many possible values, got all the decimals, and more decimal places with a better measuring tool, we call those things continuous. So we're not talking about continuous things today, we're talking about discrete things. Okay, so a probability distribution of a discrete random variable x provides the possible values of a random variable and the corresponding probabilities, often given to you in a table, etc. Okay, some reminders. These kind of happen with any probability, whether it's discrete or not. The sum, remember this fancy E thing here means the sum of all the probabilities have to add up to 1. And then when we get an individual probability, it should be somewhere between 0 and 1. Remember, if it's 0, that means basically it never happens, and if it's 1, it means that it's always happening. Okay. The mean of these, I think that this formula is given to you maybe on your pink sheet. I would not stress a lot about it. We'll do it on a calculator. But in this case, you take the values of x, which is the random variable. I would probably know that that x means the random variable. And then we multiply it by the probabilities of observing that random variable. Something to point out to you, as the number of repetitions of the experiment increases, so if we continue to do it multiple times, the mean value of the n trials, the mean of all the observations, will approach the mean of our random variable x. So in other words, if we repeat the experiment many times, we expect the mean of the observations to equal the mean of our random variable. All right, okay. Continuing on, the last thing here is another way to say the mean of the probability distribution. So think about that as like the mean of x is the expected value. Sometimes you see it with like e and then the x next to it. Remember, as we repeat the experiment more and more times, the mean of the observations approaches this value. Okay. Our standard deviation is given by the formula there. Remember, x is the value of the random variable, mu sub x is the mean of the random variable, and then p of x is the probability of that happening. Unfortunately, we were going to do the nonsense test, but since we're not together in class, it kind of defeats that purpose and it would be hard to pull it together. Maybe some point next week we could do a little bit of that as a whole class. But in the meantime, we'll do an example on the next page that we all can go through together. So, in a probability distribution, the random variable x represents the number of hits a baseball player attained in a game over the course of the season. Verify this is a discrete probability distribution. So there's two things that have to be true. First of all, we said, hey, what do the sum of all the probabilities have to equal? The sum of the probabilities have to equal 1. So, take a moment, see if that's true. If we add all these probabilities, do we get 1? And if you were to add them all, yes, you do. So that's true. And the next thing is the probabilities are between which two numbers? 0 and a 1. And is that true as you look at the list of p of x over on the right side? Notice all those are between 0 and 1. So yes, this is a discrete probability distribution. Notice also like our data is discrete things. Okay, so the distribution has a mode of, so they're saying which one's the most frequent? So I would look over at the probabilities, and as you look at those probabilities, you're saying, okay, which of these happens the most? the highest probability, I believe, is this point, I can't circle it there, let's try this, is this point like 3358. So that will be our mode, which if you look over the ones, that has the random variable of 1, so 1 hit per game. Okay, let's look at the distribution. So on here, the left side is your probabilities, right? We get the number of hits in a game, and maybe I'll be like, baseball players hits or something as a title. Nothing fancy. Okay, in this case, we usually graph it. It almost looks like a bar graph in the sense that we just make each of these heights, these bars, the probability. So like 1.6 would go about there. Sometimes they have like a little dot at the top. 0.33 would be up here. They usually just draw a line connecting it. 0.28 is about here. And then we've got 0.149. And then I've got 0.3. And then I've got 0.2. And there's nothing there at 6. So as you take a look at that, as you think about the shape, I often like to kind of like draw on top. Which way is that skewed? That would be skewed right. So let's compute and interpret the mean of this random variable. We're going to do this really, really similar to how we did it in one of our earlier chapters, when we have this as our L1, and now our frequency is going to be L2, the probability of that happening. So if you don't have a graphing calculator at home, there are some online calculators that will do this for us. I'm going to switch to my calculator real quick. All right, so remember we press Stat, and then we go to Edit. Our first list is going to be that 0, 1, 2, 3. I'm going to add 4 and 5. I guess I already had some data in there that kind of matched this. My probabilities is 0.1666, 0.3358, 0.2852, 0.1495, 0.0385, and 0.0244. So now we're going to go to stat right. In this case, we still call it one variable for our mean, but you can think about it as being like a binned or group data where we've got our list, and you will want to have L2 as your frequency, those probabilities, as how often each variable is happening. We're going to hit calculate. So remember here which of these is your mean. X bar will be your mean. And then in this case, it'll be the sigma x as the standard deviation. So let's go back to our notes. So as we take a look here, let's put in some numbers. Even though x bar is what your calculator tells you, really this is mu of x, the mean of this discrete random variable. It's 1.6307. And what that means is that over many games, so if we were to play multiple times, the baseball player is expected, right? Remember how we call it the expected value? To average about 1.6 hits per game. Maybe you'd round that up to 2. But since it is an average, it's okay to have an average of 1.6, even though we know you can't hit 1.6 hits in a game. Okay, the standard deviation was at sigma x, and it told us on our calculator it's 1.1785. Okay, so now let's talk about it. What's the probability in a randomly selected game that the player got 5 hits? So our probability that x equals 5, if we looked at that distribution up above, was 0.0244. And remember we said anything is unusual if it's less than 5%. So the question is that probability less than 5%? Yes, it is. So yes, it's unusual because it's less than 5%. Okay. Let's look at 2 more examples here. Okay, An investment counselor calls with a hit stock tip and believes the economy remains strong, as if that's happening now. Unfortunately not. The investment will result in a profit of $50,000. Okay? If the economy grows at a moderate pace, it will profit in $10,000. If the economy goes into recession, it will be a loss of $50,000. Your economics who believes there's a 20% probability it will remain strong, so 20% up here. At 70%, it will grow at a moderate pace. And then at 10%, the economy will go into a recession. What's the expected profit? So basically your mean in this case. I always think about like setting up the table because I think that's the easiest because then you kind of know what you're putting in your calculator. I'm actually going to make 3 parts of this just so we know like this is what the economy is doing to keep things straight. So they said strong, moderate, and then the recession. So in this case, we've got either a profit / loss, and then your probability will always be like the L2. You're welcome to do like 20% or 0.2. I personally like to do like 0.2. I think that makes more sense in my mind, and it then meets that criteria that it adds up to 1. However, your calculator, as long as you leave it all the same as like 20, 70, and then 10, or 0.20, 0.70, 0.10, it will handle it either of them equivalently. Okay, so if it's strong, they said you're going to get a profit of $50,000. If it's moderate, you're going to get a profit of $10,000. The hard part, they said it was actually a loss in this last one of $50,000. So I can't just do $50,000 because that's the same as a profit. So how we deal with a loss is we make that negative. All right. I'm going to let you take a moment, maybe pause the video, type that in your calculator, or if you've got like StatCrunch or another online calculator to figure out what that is. And then the expected value of X, which is equal to our mean, in this case, ends up being $12,000. Okay, let's look at one more. So, in a game of roulette, a player can place a $5 bet on number 17 and have a 1/8 probability of winning. If the metal ball lands on 17, the player wins $180. Otherwise, the casino takes the player's $180. So our 2 events is either you win or you lose. So if you lose, they take your $5, so you've lost $5. If you win, you get $180. I'll be honest, I'm not like a roulette player, so I don't know if they take your money as well, your initial $5 always, so you get kind of $175, or you just get the $180. It looks like you get your money back as well as your winning, so let's add it this time. So you've got your $180 you got from winning, plus your $5 back that you invested, so you just get $180 back. So the probability of the first one is you have a 1 out of 38 chance of winning. So if there's only 2 events, this other one is 1 minus 1/38 chance of winning. Whether you do that in your calculator, or you do a little simple math there, you're like 38 over 38 is equal to 1 minus 1 over 38. This one has a 37 out of 38 chance of winning. Once again, you can then type that in your calculator to kind of see what you end up with. Remember, you'd go to Stat, you hit your Edit, you type in, and you can do, for the record, you can type in like a fraction, and it will make it a decimal on your calculator, and that's A-OK. So as you do that, and then you hit your 1 variable stats, you end up with a mean, or your expected value, of negative 0.0036, which is approximately $0 if we wanted to think about it. In which case, the company who's kind of having you play this game is not winning or losing any money, and therefore you're not really winning or losing much money either. However, if you played 1,000 times, if we took 1,000 times that expected value of negative 0.036, you would end up technically losing. You'd get negative 3.6.